before we actually deep dive into anything, we first need to actually set the stage for actually understanding experimentations and why it is important. So let's first understand what A/B experimentation is. So let's so experimentations are essentially the bread and butter of every great product company. So you take Spotify of the world, Amazon, Meta, any company you take, at any point of time, they are running tens of thousands of experiments on their products. So at this point, I'm pretty sure we all have Instagram. None of us have the exact same app because we are actually involved in some sort of experimentation, and we belong to some cohort whose experience is a little bit different from what the general public is actually viewing. So experimentations help these companies in getting these micro gains and sometimes even launching completely new streams. So if you remember Instagram Reels, when it came out first to a very general, very small cohort, and then slowly and steadily, you actually started seeing that more and more people actually had Reels before it actually went to the general public. So that is them actually just doing A/B test or some sort of experimentation to understand how the new product is actually doing, whether whatever metrics they are tracking in terms of retention, revenue, how is it actually doing, whether it's actually doing better than previously or as compared to the control set. Now, coming generally to what A/B test is. So let's assume you want to test out a feature or you launched a new ML model and you want to see, let's assume you launched a new recommended model for Instagram feed. So now how would you actually test whether this algorithm is actually doing better or not? Because in recommenders, your offline testing does not actually reveal much because you're actually now playing with real world user behavior. So how this generally proceeds is we take a small cohort of users on whom we actually launch the new algorithm, and we'll keep the remaining or we'll take another small cohort and we'll keep them as what we call control. So the smaller cohort on which we are testing the new algorithm is the test set and the other is control. Now we'll compare between these two. We'll compare these two groups and see whether the test group is actually doing better on the metrics that we had decided for the experiment. Now, if we see yes, the metric is doing better, we'll then have to answer the question whether it's actually statistically significant or not. And if it actually comes out to be statistically significant, we'll actually now expand it to a larger cohort, and we'll keep on experimenting till we actually reach a certain cohort, let's say 25%. And at 25% probably, or depending on the company scale, like if you're at Google scale, then even at 5%, you can say that, yes, the experiment works pretty well. But for companies, you would probably then want to test it at 25% and then 50%. So, and then you can basically take a call, yes, this feature actually is doing well for overall, and we should actually go ahead and launch it. Now, one thing to keep in mind is that not all experimentations can lead to such statistically significant results, and that depends on a lot of factors. One itself being how you're actually designing the experiment, and in network effect products like Facebook and all, even sometimes when your result is saying that the difference is statistically significant, the bottom line of the user experience might get degraded. So one of the example is that like Facebook has actually launched this new feed feature in which you actually see reels in the feed as well. Now, in terms of their metric, they probably are doing great. But if you hear the general review that people are actually really, really pissed. So sometimes just because your metrics say, the retention has improved or something has, or your metrics are showing goodness, doesn't mean it's actually going to translate into great user experience. So that is the reason we actually need to always keep on continuously experimenting. So before I actually move into the next slide, I do have a question for the public. My question is, do you think can we actually experiment with more than 2 variants? So right now, if you see in the image, we only have control and variation. Is there possible that there can be test 1, test 2, test 3, test 4, test 5, test 6, test 7, and like that, and control? So is it possible or not? Anyone? Okay. So the answer is yes. So there is a technique called multi-arm bandits where you can choose multiple variations, and you can over a period of time you can see which one is performing better, and that variation keeps on getting selected more and more and more before we actually converge to one single one. So I'm not sure if you've heard of this experiment, but Google notoriously actually see something on the chat. Okay, awesome. Okay, yes. So coming back to Google example, so Google notoriously one actually selected around 40 different colors, and basically they distributed it to 2.5% of the user base, and whichever user base had more CTR, which is the click-through rate, was how they actually selected the color for the Gmail icon. So I mean that's I think a little over optimization in terms of A/B testing, but yeah, general sense being you can actually test with more than 2 variants. You can go till as many variants you want till the time you can make sure that for every test set you can have statistically significant results. So at my current company as well, we do run, we at any point of time, we are running more than 50 plus experimentation. We are nowhere near the scale of what Amazon or Facebook do, but we are trying to bridge that gap. We are basically also building our experimentation capacity and our own platform and stuff to expand it. But in general, yes, almost all product companies are always experimenting. So now moving to the next part, the problems with A/B testing. So currently, if you have, so what you are actually testing is for causality. So you have A and B, which your A being your test set, and to that you have added some sort of change to it, and you want to know what kind of impact that change is actually going to have. So A/B test, right? A/B test is right now the gold standard for actually doing that. All other methods are not exactly, won't give you 100% goodness. The reason being that when you do an A/B test, you're actually taking two populations which are completely random. Yet, if you do an AA test, which is comparing the metric of both the groups without the interference, all the metrics will almost likely come out to be the same, which we cannot say if we do a non-random cut, like you take users who have played less than, in MPL's case, like if we take users who have played a huge amount of game and we compare them to users who have played very small amount of games, our AA test will not hold because the metrics will differ. So any kind of a change we add to any of the group will likely not give a statistically significant result. Now coming to the problem with A/B testing, if someone actually in their job recently has doing any kind of experimentation, can they on the chat or just use the audio to tell me what kind of problems they face while actually doing an A/B test? Okay. Okay. So let's discuss about some of the problems that we can have while doing an A/B experiment. So remember, whenever we can actually do an A/B test, we should always do an A/B test because it is the gold standard and it is the most likely to give us goodness in our results, where we can basically conclude whether there was actually a difference between the groups or not. So the first point being that the causal impact to be tested is not in company's control. Okay, so a simple example is, let's assume you are a cloud provider like AWS, and you actually make some change to one of your algorithms that you're using for your ML models and all. Now, but you are providing the service to the end customer. So how the end customer uses it, the data is not in your control. So it's going to be extremely painful for you to actually do any kind of A/B test on this. Next is that when actually doing an A/B experimentation actually can cause more harm than good for the company. So let's assume this problem is very specific to MPL, that we had this problem that should we actually A/B test whether an ad during IPL actually brings us a boost or not. So now we can A/B test it, but it's going to be extremely painful for the company, and there is also a huge missed opportunity for us if the A/B test actually comes out to be statistically significant. So these things we do not usually test. We settle with what the business actually has in mind. Then coming to the legal or the ethical issues. So let's assume you are doing a drug test, and basically now the issue is that you cannot actually withhold information from the control set. So if let's assume you have a cancer, like a cancer curing drug, and both the groups have cancer, so you cannot give the cancer saving drug to one group and not to the other group without their consent, obviously. Then the fourth point is when proper randomization is actually tough to perform. So a lot of times it's actually not possible, depending on the scale, also depending on how big your company is, or just how the user actually come on the platform. You might not be able to actually properly randomize the group. So a very good example being that let's assume you are testing a new feature, and you basically have only 100 people live on the on that feature. So it's actually impossible to do a proper randomization here. And the fifth being when it's actually technically not feasible to perform an A/B test, and I'll discuss about this in the coming slides when I actually tell you how at MPL we were using quasi experimentation. So now the next question that I have is what is the power of the experiment? Can someone answer that? Okay. So by power of the experiment, what we mean is what is the number of users or the number of recordings you need to determine statistical significance of the experiment. So you have your test and control, but at what point will you say that given your baseline and you want to see a 2% improvement in your baseline from the baseline, how many recordings will you actually need to make sure that the results that you will get is statistically significant or not? So that is what we call power of the experiment. There are a lot of online calculators for this. You can just Google A/B test power calculator and just input your baseline metrics and how many users you have on the platform, and that will give you the answer. So this is a very good image from Spotify. From Shopify's blog. So this is basically gives you the hierarchy of evidence. So at the, for experimentation, for basically knowing the statistical significance of an experiment. So at the top, you can see we have A/B testing, which is like the gold standard for doing it. After that, we have causal experiments, quasi experiment, which we will be talking about today. And then there is counterfactuals. Does anybody know what a counterfactual is? Okay, so a counterfactual is generally basically we try to so let's assume we already have a group and we make an intervention to that group. So a counterfactual is usually an alternate reality, basically, such that if the intervention would not have happened, how the metrics would have looked like for that specific group. So that's a counterfactual. So yeah, now coming to quasi experiments. So quasi experiments are experiments in which we cannot actually truly randomize on the control and test group, but we use different methods such that we can actually bridge the gap between the test and control. And in some cases, there will not be a test at all. Sorry, there will not be a control at all. And we will still try to basically measure how the metrics are doing after the interventions that we have made. So today we'll be discussing about two techniques. Both of the techniques we actually use at MPL fairly regularly. First being interrupted time series, and the second being difference in differences. So before we actually move on to doing quasi experiments, understanding more about quasi experiments, one of the biggest pitfall of quasi experiments, as it might be fairly easy to understand, is having unwanted confounders. So by confounders, what I mean is these are some unmeasurable variables that are present that might be affecting your experiment, which you have not taken into account. And they are actually the ones that are causing the results to skew. Even though, and this is actually happening because we have not done a true randomization between A and B. If it was a true randomization, this would actually not be happening for us. because both the groups are equal for us. So as you can see in the image, and this is a very well-known image. So there is basically an experiment in which basically we were trying to detect what is the life expectancy of a human given his palm size. But the confounder here, the confounding variable here is gender. Now it actually came down to this, that if you're a woman, and you'll probably have on an average smaller palms than a man, and you are actually going to live much longer. So here actually gender plays a much bigger role than the palm size. So this is how confounding variables can actually completely skew your understanding of the experiment. So this is one of the biggest pitfalls of actually using quasi experimentations. And while we actually design the experiment, we have to make sure that we actually know about these so that we can actually take care of them. Yeah. So coming to the first method, and this is quite a simple method to perform. And if you are actually like working and you do deal with experimentations on a daily basis, I would actually recommend you to read more about this. So in an interrupted time series, what we do is we usually do not have a control. So the image that I've picked is from Netflix and how they do quasi experimentation. And I'll later in the slide show how we can actually decide on a control region. But usually how this works is, so let's assume you have a you have a time series of, let's say, signups. So, and you want to make a marketing intervention, and you want to see what kind of uplift this marketing intervention can actually bring you. So what you do is you keep you basically do not make an intervention for some time, and then for some hours you actually make an intervention, and then you see what your metrics actually look like, and then you again close your your intervention, sorry, and then you again see what your metric look like. So if you see what is happening in the chart here, that once they introduce an intervention, the blue line actually starts going up, and once they actually remove the intervention, the blue line again comes down. So if we keep doing this again and again and again and keep collecting data, after some point, we can actually average this data out and say that there is actually a net positive in actually including this intervention for that specific group. Now, so this is what we do actually at MPS. So we have a pretty complex matchmaking system. And by matchmaking system, I mean how we actually match two players on the platform if they are coming to play the same game. So we had to now introduce a better matchmaking algorithm so that users can have a better experience. Now, the problem with doing A/B tests with a matchmaking system is, like, even if I do a 50-50 split, I'm going to actually reduce the concurrency, which is basically the number of users we have on the platform, by 50%, which is actually going to shoot up our wait times. So A/B test here is not possible. So how we actually go about doing so we call our ML algorithm module 1. So for 2 days, we actually run our ML algorithm. And then for the next 2 days, we run our base algorithm, which is the ELO algorithm. And then we again run our module 1, and then we again switch it off. After this time span has passed, we actually now have data of how that same group is actually doing when the module 1 runs versus when the module 2 runs. Now, of course, there will be users coming and going, and a lot of things might be happening on the platform in terms of pricing or marketing. But if we average it out, this usually gives us a statistically significant result if we run it for a possible decent enough time interval. So MPL thankfully has a decent user base. So we are able to usually conclude this experiment in 10 days, which is still a huge amount of time, but that is basically what we have found, the number of days we need to basically have a statistically significant result in terms of power of the experiment. Now, the problem with this kind of experimentation is that it's easy to attribute some of the metrics which are very straightforward. Like, of course, the matchmaking system affects our D1 retention and our win rates. So those are fairly straightforward to calculate. But what if you want to study long-term metrics like your day 7 retention or your monthly retention and stuff like that? So this system actually makes it extremely hard to actually do those kinds of metric tracking. So if you want to do those kind of metric tracking, again, you'll then have to run it for 15 days and then close it for 15 days again. But usually as the time period increases, the bias also increases. So to make sure uh, like these experiments actually produce worthwhile results, it's always good to actually only focus on metrics which you can track on the same day or the next day. So yeah, the second method being difference in difference. So this is also again a fairly straightforward method, but here let's assume you cannot find a control, you cannot do a randomization. So you actually now try to find a control group which is very near, which is very similar to the group to which you actually want to make an intervention to. So let's assume now you have done some calculations. We'll talk about what kind of calculations you can do to find that close by group. But let's assume you have found that group. Now you have that group and you also have the group on which you want to bring an intervention to. Once you actually bring an intervention, whatever uplift you see from the baseline can be attributed to the interventions that we have made. So this is basically fairly straightforward. So in the image, you can see group A, and in the and there's also group B. And the red line is basically when we actually introduce the intervention, and we see an uplift in group P metric, and that is what, and that lift is basically what we are attributing to the intervention itself. Yeah. So now coming to what kind of metrics you can basically track. So one itself is a business metric, and if you know from basically your domain knowledge or something that this game is very similar to the game. So sorry, not game. So in our context it's game, but in your context it can be anything. It can be two states, number of vehicles or stuff like that. So your first thing is your domain knowledge comes into play. So here, I'll take the example. So we have one game called Fruit Shop, and what we basically believe that the in the starting that the statistics of Fruit Shop and the general user base who plays Fruit Shop also plays these other games. So this is how we actually reduce the universe, because we have more than 50 plus games. So of course there can be some spurious correlations as well, which we wanted to remove. So the first thing we did was we used domain knowledge. Then the second is we see correlations of metrics like CPDOG, which is basically what we call a cash playing daily user who actually basically invests in the platform and plays the game. And then there is PDA, which is basically users who just play a game with or without money. And then there is basically GP means number of games played in a day, correlation between the series. And RE basically stands for retention. So how the D1 retention actually looks like. So once you have this information, the other thing we can do is check for co-integration. So I'll talk about co-integration and I'll keep it as an open question. We check for co-integration between these series as well. So once you have both the information from co-integration as well as your correlation metrics, you can now decide on which game, at least in our case, which game is actually closest to Fruit Shop. Once we have that game, we then say that this is the control group now, and we can compare Fruit Shop with this, and any intervention we bring to Fruit Shop, and if we see an uplift, can be attributed to the intervention. Now, coming back to this diagram. So what Netflix did was they actually combined both interrupted time series and difference in difference. So they first chose a group which was very near to control, which was very near to test, and then they started basically making interventions to both the groups, and they started then recording how the both test and control are doing. So by having a control to an interrupted time series, they are basically able to remove any level of bias that comes from the platform itself. So again, it could be, so because it's a network effect product again, so some marketing in some other region or for some other game can actually heavily skew results for Netflix as well. So that's why they actually decided on having a control as well. Yeah. Coming back to the question of co-integration. So I would like to open this to the general public, and especially to people who are actually very interested in stock market and stuff. So can someone explain what co-integration of two time series actually is? Okay, this definition might be right, but I actually cannot understand what this actually means. So probably if someone can come up with a much more uh, simpler explanation, that would really help. Okay, how many of you have actually heard about pair trading? It's a very common trading algorithm technique.
Maybe in simple terms, we can say that is a technique used to find possible correlation between time series process in the long term.
Okay, okay. Yeah, it is sort of correct. It's just missing one property, which I'll discuss, but I'll just wait for if someone actually wants to pitch in. I mean, if you actually invest in stock markets, then I'm expecting that you probably know or probably have heard of co-integration and pair trading. So my simple question is, so you have two time series, right? So I want to know whether they are co-integrated or not. Now the question comes, what actually is co-integration? How can we, when can we say that the two time series are actually co-integrated?
We can say that if one time series is increasing, then another one is also increasing with the same
Okay,
time.
okay. But but that's basically, so it could easily be that two time series are actually trending upwards, but they're still not correlated, or two time series are actually trending downwards and still are, and they're correlated, but they are not co-integrated. So let's try to understand what's happening. So the first image, if you see, uh, the blue line and red line, to clarify your doubt, so both of them, do you say that they are positively correlated? So they are actually positively correlated because if you do any kind of PSN coefficient test or whatever correlation test you use, they will come out to be positively correlated. But do they move together? They actually don't, because we see a dip in the blue series, which is not there uh, in the pink line. So now these basically time series are actually correlated but not co-integrated. Now, if you see the second image, we can see that both the uh, time series actually are correlated, but they also move together in time. So once the blue line drops, the red line also drops. So just to basically sum it up, uh, the line blue can be actually defined by basically as a process of basically the red line into some uh, coefficient plus some noise. So that is when we say that two time series are actually co-integrated with each other. So in the previous slide, so there are a lot of statistical tests that you can use. They are fairly straight. They are available in almost every Python statistical library. So I'm not going to jump into them. But usually we do use co-integration with correlation so that we do not actually have such spurious relationships like I showed in the first image, and we can eliminate them. So here, even in the image, you see a lot of the uh, time series which were extremely correlated actually didn't have a very significant p-value. So we actually have to reject those series that they are actually co-integrated with each other. So yeah, that's about. So that's from my side, and I share with you the slides, and I've attached a lot of links there from where you can study about more about causal experimentations. And I would now like to open it to everyone for Q&A. And yeah, if you want to connect with me, you can connect with me on Twitter. I'm usually the most active there. Yeah, we can start with the Q&A. Okay, so the first question is, what is co-integration? Like I explained, two time series can be said that, so if you want to look at it visually, two time series can be said to be co-integrated if they move together. They can move in the same direction or different direction, but if one time series falls, the other time series also falls, or if one time series goes up, the other time series also goes up. So in short, the one time series can be defined as the coefficient of the other time series plus some noise. Okay. Second question is, can we use uplift modeling and causal ML instead of A/B test? So you can use causal ML. So even we have tried causal ML, but one of the problems with actually using causal ML is that you have to be very, very sure of the confounding variables, because in causal ML, you are basically trying to uh, predict what the basically what would have happened without the intervention. So that is at least what we have seen. We cannot actually do a very good prediction there because of some of the other underlying confounding variable which we have not taken into account. So, but yes, you can use causal ML. Can you know industry standard A/B testing tools? So there are as such no industry standard A/B tools. So there is Optimizely and there is CleverTap and all, but all they provide you is the infrastructure to do A/B test. But in the end, you are the one who has to design the experiment in a way that you can actually track the results. So and it's going to differ company to company. Should I run co-integration tests? Yes, you should definitely run co-integration tests. So I don't exactly remember what the statistical test name was, but there are a lot of statistical tests available for co-integration testing. Difference between VAR and VECM model. I am not sure of what VAR and VECM model actually means. How to eliminate effect of confounding variables. So one easy way is, again, try to find a way in which you can do an A/B test. That is like the gold standard way of actually eliminating effect of confounding variables, because you cannot always control all the confounding variables. The other way is that if you have a lot of, so let's assume in our case, uh, so I showed the fruit shop example, and we have a lot of other games. So we can try defining the time series of fruit shop as a combination of all the other time series or some of the time series which are actually related to the fruit shop one. So in that case, we average out the effect of confounding variables from the other time series. So that is one way. Basically, these are the two ways which I know of in which you can eliminate the effect of confounding variables. But will not always be able to control these. In which platform you are currently doing A/B testing? So we use something called CleverTap, but CleverTap only provides us uh, with the ability to basically define groups of A and B. So we basically choose how many users we want in the test group versus how many we want in the control group, and we basically then get this data in basically in our Hive tables and all, and then we can do all the calculations of metrics that we want. So as such, we don't have an automated way in which we can basically define from a platform the split, and it will also give us how basically the test is doing, right? But there are one or two platforms. I'll actually just write here. It's called basically Get Apo. It's called Get Ebo. I'm not able to write for some reason, but it's called Get Ebo. So there they basically provide a whole suite of platform where you can actually do where basically they start with actually defining the A and B cut and also doing all the metric calculation that you want. Any other questions? How to test for randomization in an experiment? Okay, so I'll try to answer the question to the best of my ability. So how to test for randomization? So I'm assuming you mean how to test whether the groups are truly random before you actually start your A/B experiment. So that is fairly straightforward. So whatever test that you define versus whatever control you define, you actually check on some of the base metrics that you have. So every company usually has some base metrics in terms of retention or their daily activeness or something like that. So you try to see that the difference between these two sets in terms of metrics is as small as possible. And you'll have to define basically a threshold that above this, we cannot say that these two groups are actually truly randomized. Can we try Causal next library for different product features and do intervention to check its effect. I'm not sure of the Causal Next library. I've never used it, but again, before you actually like try to launch a feature, you should always take a good amount of time with stakeholders and everyone and your data teams and stuff that to define how do you want to actually experiment the launch of the feature. So like doing an intervention is one type of experimentation. There are lots of other experimentations available. So it depends on the context of what product you are launching and how you can actually basically define the experiment. So before you actually launch a feature, you should spend a good amount of time basically deciding how we'll actually experiment. So at least at MPL, before we actually launch a feature, we do have a like a basically an hour-long discussion with the PMs and all the other data science involved, where whoever is leading it from the data science team, presents how we are actually going to experiment the feature and whether this is the correct way or not. So that's how usually we decide how to go about launching an experiment for a feature. Suggest any article on this topic. So I have attached these in the PPT. So I'm sure that Ram will take care of sending these. In any case, you can reach out to me and I will share you the list of articles. The tool for, okay. So the tool that I was talking about was GetAbo. So they basically do the calculations for test and control for any GNN use case. So by GNN, I'm assuming this is called graph neural network. So yes, we do have a use case in catching fraud for graph neural networks. In fact, we do have a graph neural network live for catching fraudsters on the platform. Any other questions? So tool for A/B testing, Optimizely and GetAbo, I have written in the chat. So I'll just wait out for next couple of minutes before we wrap up. So if anyone has any other questions, they can ping on the chat. Okay, great. Thank you so much for joining. It was a pleasure taking the webinar. And if you have any more questions, you can definitely connect with me on Twitter.